Giant ancient structure we can't replicate with our technology. Uluru, the dead centre of Australia, hundreds of kilometres from the nearest town, one single solid piece of rock rises out of flat red desert like nothing else on the continent. It stands taller than the Eiffel Tower would if you cut off its antenna. It stretches nearly 6 kilometres around its base, and for more than 500 million years, it has done something almost nothing else exposed on the surface of the Earth has managed. It has refused to wear away. Every geologist who spends real time studying Uluru eventually runs into the same uncomfortable question. We understand rock. We understand erosion. We understand how wind, rain, and heat grind stone down into sand over millions of years. So why is this one piece of stone still standing, still mostly intact, while everything around it, for hundreds of kilometers in every direction, was worn down into flat plain long before the pyramids were ever imagined? Some visitors ask if it was built. It was not. But the real answer for how Uluru survived turns out to be stranger and more scientifically interesting than most of the popular claims made about it. Today, we are walking through what modern geology, basic material chemistry, and Aboriginal knowledge, older than written history, can tell us about the giant red formation sitting at the heart of the Australian continent. Before we get into how Uluru actually formed, and why one very popular claim about what lies beneath it turns out to be a myth, geologists have spent decades trying to correct. If you enjoy real Australian stories, told with the actual science behind them, instead of the exaggerated version, take a second to subscribe. It helps this channel keep digging into places most people have only heard half the story about. Uluru sits inside Uluru-Kata Tjuta National Park in the southwest corner of the Northern Territory, close to the town of Uluru, and roughly 450 kilometres by road from Alice Springs, which is itself already deep in the interior of the continent. There is no coastline nearby. There is no mountain range feeding it. There is just flat spinifex desert stretching to the horizon in every direction. And then, without warning, this. The numbers alone are worth sitting with. Uluru rises 348 metres above the surrounding plain. Measured from sea level, its summit sits at 863 metres. Its circumference at ground level runs to about 9.5 kilometres, meaning a full walk around the base takes most visitors between 3 and 4 hours. It is a single, continuous mass of rock, not a cluster of boulders, not a ridge made of many smaller outcrops fused together. One body of stone. The summit itself is broad enough that surveyors originally mistook it for a larger mountain range. To understand why that single body of stone is still here, you have to go back more than 550 million years to an event geologists call the Peterman Orogeny. Long before Uluru existed in anything like its current form, Central Australia was the site of a slow, grinding mountain building event. Ancient tectonic plates pushed against each other, and a range of mountains rose up in roughly the same region where the flat desert now sits. Mountains that rise also erode, and this range was no exception. Rain and wind tore into the young peaks almost as fast as tectonic forces could lift them. The debris, sand grains rich in feldspar, mixed with quartz, washed down off the mountainsides in huge alluvial fans and collected in a shallow inland basin known today as the Amadeus Basin. Over millions of years, that sand compacted under its own weight and under the weight of everything deposited on top of it, cementing into a coarse, feldspar-heavy sandstone known as arkose. Arkose is the first part of the answer to why Uluru still stands. Most sandstone is dominated by quartz, which is chemically stable, but forms grains that do not lock together, especially tightly, once the cementing minerals between them start to break down. Arkose is different. Its high feldspar content means the grains interlock more densely, and as those feldspar grains slowly weather, they release clay and iron compounds that act almost like a natural adhesive, binding the remaining grains even more tightly together. In effect, the rock strengthens some of its own surface as it ages, instead of simply falling apart. The next part of the story is about orientation, and it is genuinely strange if you have never thought about it before. Those original sand layers were laid down horizontally, the way sediment normally settles. But later, tectonic activity, additional compression from continued plate movement, tilted the entire rock formation on its side. Today, the sedimentary layers inside Uluru run almost vertically at close to 85 degrees from horizontal, rather than lying flat the way most sedimentary rock does. That near vertical tilt matters enormously for erosion resistance. When sedimentary rock lies flat, water can seep between the horizontal layers and slowly pry them apart from the top down. The way pages peel off a stack of paper. When the layers stand on their edge instead, water has almost no horizontal seam to exploit. Rain runs down the near vertical faces of Uluru rather than soaking into flat bedding plains, which is part of why the rock has held its shape so well for so long, while the surrounding softer material simply washed away, grain by grain, over hundreds of millions of years, leaving Uluru standing alone. That brings us to colour, because the deep red most people associate with Uluru is not actually the true colour of the rock underneath. If you could find a freshly broken, unweathered piece of the sandstone, it would look pale grey, close to the colour of ordinary concrete. The red comes entirely from the surface. The feldspar in the arkose contains iron, and over immense stretches of time, that iron has oxidized, essentially rusting. The same basic chemical reaction that turns an old iron nail reddish-brown. That thin oxidized layer is what gives Uluru its famous glow at sunrise and sunset, when low-angled light makes the iron-rich surface appear to burn. Now, for the claim that gets repeated more than almost anything else about this rock, and the one that is, according to working geologists, simply not true. You have probably heard some version of it. The idea that Uluru is like an iceberg, that what tourists see above ground is only a small fraction of a much larger mass, sometimes said to extend 2 or 3 kilometers straight down into the earth. It shows up in guidebooks, in old school textbooks, and in plenty of documentaries that should probably have checked their sources. Geoscience Australia and geologists who have actually mapped the Amadeus Basin have been trying to correct this for years. Uluru is not a deep, vertical plug of rock sunk far into the crust like some kind of stone iceberg. It is the exposed edge of a folded layer of sedimentary rock, part of the same tilted arkose bed that also forms ridges elsewhere in the basin, some of which stay buried and some of which happen to break the surface here. Subsurface studies using gravity and magnetic survey data do suggest the rock body continues down for some real depth, but nothing close to the dramatic multi-kilometer iceberg figure that keeps circulating. The true story, a folded sedimentary layer shaped by hundreds of millions of years of tectonic pressure and selective erosion, is arguably more interesting than the myth, even if it is less cinematic. The tools geologists actually use to check what lies beneath Uluru are worth understanding, since they explain how scientists can make confident claims about subsurface rock without drilling straight through a sacred site. Gravity surveys measure tiny variations in the strength of Earth's gravitational pull across an area. Variations caused by differences in the density of rock lying underground, since denser material exerts marginally more pull than lighter material sitting at the same depth. Magnetic surveys work on a similar principle, detecting how different rock types distort the planet's magnetic field in small, measurable ways. Combined with existing knowledge of how the Amadeus Basin's sediment layers fold and tilt across the wider region, these non-invasive methods let researchers trace the arkose sandstone bed well beyond the visible edge of Uluru itself, without needing to disturb the rock or the land around it, which matters enormously given the site's protected cultural status. So, if it is not a buried iceberg, why does the framing of an ancient structure we cannot replicate still feel accurate, even once you strip out the myth? The honest answer is about process rather than mystery. Uluru was never built the way a monument is built, stone by stone, with an architect and a deadline. It was built the way almost nothing modern engineering ever gets the chance to build anything over 550 million years, through an unrepeatable combination of exact sediment chemistry, exact tectonic timing, and exact erosion patterns that all had to line up in sequence for this specific outcome. Modern materials science understands each individual ingredient. Nobody can compress that ingredient list back down into a human timescale. There is a specific process worth pausing on here, because it is real material science, and it explains why Uluru is not just old, but unusually good at staying intact. It is sometimes called case hardening, and it happens in dry, harsh climates, when water-carrying dissolved minerals rises to the surface of a rock through capillary action and then evaporates, leaving behind a thin, extremely hard mineral crust on the outside, almost like scar tissue. That crust is often denser and more erosion-resistant than the softer rock sitting just beneath it. Uluru's surface shows evidence of exactly this kind of hardened rind, built up slowly by desert conditions rather than applied all at once, which is part of why current erosion rate estimates for the rock sit at only a few millimeters lost per century, a pace that is almost impossible to picture on a human scale. Engineers today study case-hardened natural surfaces like this one because they behave almost like a self-reinforcing coating, strengthening exactly where exposure is highest. Concrete, by comparison, typically starts degrading within decades in harsh climates without constant maintenance, since it has no equivalent process for repairing or reinforcing its own weathered surface. That gap between a natural process running for hundreds of millions of years and a manufactured material struggling to last 1 century is the real, defensible version of the claim that we cannot replicate what Uluru is doing. Roughly 40 kilometers to the west sits a second, related formation that most visitors see on the same trip. A cluster of 36 domed rock formations known as Carter Tuta, sometimes still labelled on older maps by its colonial name, the Olgas. Carter Tuta formed from the same broad tectonic event as Uluru, but out of a different rock type, a coarse conglomerate packed with rounded pebbles and boulders cemented together rather than fine-grained sand. Its tallest dome, Mount Olga, actually rises higher than Uluru itself, reaching 546 meters above the surrounding plain, though its shape as separate rounded domes, rather than one continuous ridge, spread across a much wider footprint, makes it read as smaller in most photographs, even though the underlying geology tells a different story. Uluru is not actually unique in kind, even if it is unmatched in fame. Geologists have a specific term for isolated rock hills, like this rising abruptly out of a flat eroded plain, calling them Inselbergs, German for island mountain, and a related term, Bornhart, for the domed variety, often formed through very similar processes of differential erosion around a resistant rock core. Sugarloaf Mountain, overlooking Rio de Janeiro, is one. Stone Mountain in Georgia in the United States is another. What sets Uluru apart from almost every other Inselberg on the planet is scale combined with isolation, since most comparable formations sit within mountain ranges or near other outcrops, while Uluru rises completely alone from genuinely flat desert in every direction, with nothing else nearby to soften the visual impact of its size. The first recorded European sighting of Uluru came in 1873, when explorer William Gosse spotted the formation during a survey expedition into Central Australia and named it Ayers Rock, after Sir Henry Ayers, who was serving as Chief Secretary of South Australia at the time. Gosse had no way of knowing the site already carried tens of thousands of years of continuous cultural and spiritual significance for the Anangu, since European exploration of the interior, at that point, still largely treated the landscape as unclaimed rather than already deeply known. The formal dual naming, Ayers Rock and Uluru, was adopted in 1993, and in 2002, the order was reversed to make Uluru the primary name, with Ayers Rock listed second, a small but symbolically significant shift that mirrored the broader land handback process already underway. None of this geology exists in isolation from the people who have lived alongside it the entire time modern science has been trying to catch up. For the Anangu, the traditional owners of this land, Uluru is not simply an old rock formation. It is a living record of Chukupa, often translated as the dreaming, the ancestral lore and creation narrative that explains how the landscape itself came into being and how people are meant to live within it. Specific caves, waterholes, and rock faces around Uluru correspond to specific ancestral stories, some of which are shared openly with visitors, and some of which remain restricted, gender-specific knowledge, passed down only within particular family lines. One of the publicly shared Chukupa stories associated with Uluru centers on Kunia, the Woma python woman, and Liru, a venomous snake man, and it is told openly to visitors, partly because it directly explains specific physical features on the rock itself. According to the story, Kunia travelled from far away to protect her nephews at Mutitjulu waterhole, and after a violent confrontation with Liru, grief and fury drove her into a fight that left permanent marks on the landscape, marks that the Anangu still point to today in the folds, scars, and dark streaks running down that section of the rock face. Rangers who lead cultural walks around the base explain that these are not decorative legends layered on top of a rock that would otherwise be geologically neutral. For the Anangu, The physical scars and the story are the same thing, a single continuous explanation of why the landscape looks exactly the way it does. Sites like Mutitjulu Waterhole and Kanchu Gorge are not just scenic stops. They sit inside a network of songlines, ancestral pathways of story and lore that stretch across enormous distances of the Australian interior, connecting Uluru to other sacred sites hundreds of kilometres away in an unbroken chain of oral tradition that almost certainly predates the geological understanding we now have of the rock by tens of thousands of years, since Aboriginal people are believed to have lived in this region for at least 30,000 years and quite possibly much longer. In 1985, ownership of Uluru and the surrounding national park was formally handed back to the Anangu by the Australian government, with the land then immediately leased back for joint management between traditional owners and Parks Australia, an arrangement that continues today. For decades after that handback, tourists could still climb Uluru along a chain bolted into the rock, despite the fact that the climb crossed directly through a sacred, restricted area and against the explicit, repeated wishes of the Anangu, who asked visitors for years simply not to climb, framing it the way most people would frame a stranger climbing on a family memorial. That climb was permanently closed to the public in October of 2019, following a unanimous decision by the park's Joint Management Board. The closure came after years of advocacy from traditional owners and after visitor numbers to the site had somewhat counterintuitively continued rising in the lead up to the ban, as people rushed to climb before it became impossible. Since the closure, the primary way to experience Uluru up close is the base walk, along with ranger-led cultural tours that explain specific sites and stories the Anangu have chosen to share publicly. All of this tourism infrastructure exists at a deliberate distance from the rock itself. The resort town of Ulara, where almost every hotel, campground, and restaurant serving park visitors is located, was purpose-built in the 1980s, specifically to move accommodation away from the immediate base of Uluru, after the original visitor facilities, sitting close to the rock, were judged both environmentally damaging and culturally inappropriate. Ulara sits about 15 kilometres from Uluru, connected by a shuttle road through the park, and its entire layout, water supply, and waste management system were engineered from scratch for a town whose sole purpose is supporting tourism to a single geological formation, making it one of the more unusual planned towns anywhere in Australia. Uluru and Kata-Tayuta National Park holds dual UNESCO World Heritage status, recognised both for its natural values, the geology, the ecosystem, the sheer scale of an ancient landform, surviving essentially intact, and separately for its cultural values as one of the relatively small number of sites worldwide recognised for continuous, living indigenous cultural significance rather than for ruins of a culture that no longer exists in the same place. That dual listing, granted in stages between 1987 and 1994, remains fairly rare among World Heritage sites globally. The desert surrounding Uluru is not empty in the way it first appears from a distance. Desert oaks grow scattered across the plain, trees capable of sending taproots down more than 30 metres to reach groundwater, an adaptation that lets them survive years between meaningful rainfall. Spinifex grass, tightly bunched and needle-sharp, dominates the ground layer and provides shelter for reptiles, small mammals, and birds that have adapted to a climate where summer daytime temperatures regularly climb past 45 degrees Celsius, while winter nights can drop close to freezing. Rain is rare, but when it does arrive in real quantity, water sheets down Uluru's near vertical faces almost immediately, briefly turning the entire rock into a series of temporary waterfalls, a sight most visitors never witness, since it depends entirely on rainfall timing. A smaller, stranger phenomenon connected to Uluru is worth mentioning honestly, since park rangers deal with it constantly. For decades, visitors took small pieces of rock or sand from the site as souvenirs, and a significant number of them later mailed the pieces back, often accompanied by letters describing a run of bad luck they blamed on removing something from the land. Rangers refer to these as sorry rocks, and the park receives a steady trickle of them every year. Setting aside personal belief about the letters themselves, removing any material from Uluru has been illegal since the site came under national park protection, both because it is a protected natural area and because, for the Anangu, physically taking pieces of the rock is taking pieces of a sacred, living site. Scientists continue to study Uluru today, not because there is a hidden chamber or a lost civilization waiting to be found beneath it, but because the rock itself is a genuinely useful, natural laboratory for understanding long-term erosion processes, desert weathering chemistry, and how sedimentary basins record hundreds of millions of years of tectonic history in a single readable cross-section. Current research includes monitoring water flow patterns after rare desert rainstorms, when temporary waterfalls briefly appear on Uluru's usually dry faces, and tracking how case-hardened surfaces respond to the increasingly extreme heat cycles the region has experienced in recent decades. Modern researchers have also begun using drone-based photogrammetry to build extremely precise, three-dimensional models of the outer rock surfaces, allowing them to compare scans taken years apart and measure actual erosion at a level of detail that ground-based surveying alone could never achieve. So the giant ancient structure we supposedly cannot replicate turns out to be exactly that, just not for the reasons the clickbait version of the story usually claims. There is no buried iceberg stretching kilometers into the crust, and there was no ancient builder shaping stone by hand. What actually happened is arguably more remarkable. A specific mineral recipe, tilted into a nearly vertical orientation by tectonic pressure, then slowly armored by its own chemistry over 500 million years of desert sun, standing today as both a working geology lesson and a living sacred site for the people who never stopped calling it home.